Okay, good morning, everyone. Quiz on Monday based on mesh current analysis. Again, by now, students should be familiar with the routine, right? Every Monday we have a quiz, and the topic of assessment would be a topic from the previous week, the preceding week. So in this case, it'll be mesh current analysis. We'll have one topic today, which is superposition. So we will introduce the topic, talk about the theory a bit, and then cover an example problem. And then superposition homework has two problems, both of them rather straightforward. I will go over the homework problems also in class, and you would be able to knock it out in less than 30 minutes. So if you want your weekend free of circuit analysis, you can get it done today itself. Well, outside of studying on Sunday night. Okay, so let's go to the class notebook, and the homework also should be in there. Let's first look at superposition. Okay, switch sections. All right, superposition principle states that the voltage or current that appears in any part of the circuit is a result of all of the sources working together at the same time. Okay, so we can simply break up the circuit into individual pieces, into simpler individual pieces, and to calculate the voltage or current independently, and then sum them all up at the end. What it actually means is basically, let's say, take an example of a circuit that has a voltage source Vs and a current source Is, for instance. And let's say 4 resistors, R1, R2, R3, R4. Well, the voltage across any one of these resistors or the current through any one of the resistors would be a result of both Vs and Is working at the same time, right? Superposition principle states you analyze a circuit with only one source working at a time. So we have Vs on, Vs would be off. You analyze the circuit with Vs working, calculate the voltages and currents. Then for the second part of the analysis, you have Is active and Vs inactive. And then you calculate all the voltages and currents due to Is active. Resulting voltage and current in any part of the circuit would be a sum of both of those analyses. Make sense? At least the principle, not the technique right now, but the principle. Okay, that's what superposition principle is. So if you have a voltage or current, and I have the variable I chose is R. I don't know why I chose R, but it could be any variable, X, Y, Z. And that variable represents either voltage or current. Well, a resulting voltage or current in the circuit, R, would be a result of R1 plus R2 plus R3 plus so on and so forth, n number of times for n number of sources. Okay, so you break up the circuit analysis into multiple pieces, and each piece or each portion is basically just one source working at a time, or one source active at a time. All the other sources are inactive. Thus, your analysis is easier. Okay, thus your analysis is easier. So for n number of sources, you have to perform n number of analyses. It'll make more sense when we actually do an example, but at least in theory, is the principle clear? So when we say active and inactive, what do we mean? Active and inactive means we reduce the value of the source to 0. For a voltage source, so let's say inactive would mean reduce value of the source to 0. For a voltage source that is connected between 2 points, let's say Vs This is voltage source Vs. It is connected between A and B. Well, when you're performing theoretical analysis, we can change the circuit based on certain assumptions, right? So in this case, if we wish to reduce the value of Vs to 0, meaning the voltage between two nodes to 0, we can simply connect those two nodes together. If those two nodes are connected together, then they're the exact same potential. Voltage between those two nodes is 0 volts. So we remove the voltage source from the circuit. Oh, not an arrow. And we place a wire in its place. That wire is technically known as a short circuit. Short circuit simply means a wire. That's all it means. And therefore, Vs now has a value of 0 volts. So making a source inactive means reducing its value to 0. Reducing a source to 0 for a voltage source would mean replacing it with a wire. And if we extend that to a current source, current needs a pathway to flow. Current needs a closed pathway to flow through. So if it's two nodes and you need current to flow from node A to B, all you have to do is break that pathway open. If there is no pathway, current cannot flow through, hence current source is reduced to 0. Does that make sense? Just think on that. Let me know if you have any questions. So again, voltage source is replaced with a wire. A wire would join both nodes together. Both nodes are joined together, then the voltage between those two nodes is equal to 0 volts. The same concept extended to a current source means we replace the current source with an open circuit. And I was too hasty. This is current source IS. So voltage source is replaced with a short circuit wire. Current source is simply removed from the circuit. Open circuit, no pathway for the current to flow through. All right, questions? We can all slow down a bit now. First 2 weeks are over. First 2 weeks especially felt rushed to everyone. There was a lot of comments about it. But again, the reason is we have to get those, that material needs to be refreshed. The prereq material, because it's been a while for students, and that's why the first week feels especially rushed. Now we can slow down and go at an easier pace. Questions? Does that make sense? The concept of replacing a voltage source with a wire and replacing the current source with an open circuit. In both cases, we are reducing the source to 0, meaning we are turning it off, making it inactive. How many of you are taking the lab? Okay, so in the lab, this is the next week's experiment where you would use dual power supplies and you would connect to both power supplies into your circuit. And it will state, even outside of the lab, if you read the words, short out the terminals of the power supply. It's not asking you to actually short out the power supply. Okay, don't do that. What it's asking you to do is to remove or disconnect the power supply from the circuit, and you short out or place a wire where the terminals of the power supply were connected. So you're shorting out the place on the circuit, not on the power supply. So it states this in the lab write-up, and your instructor will also go over this, but I'm letting you know right now, as an engineer, whether you're taking the lab or not, if you ever read or hear the words, short out the power supply, reduce it to zero. In real life, you're not shorting out the actual power supply, you're shorting out the circuit, the place where the power supply is connected. Okay, that's what it means. So you remove the power supply from the circuit, and the place in the circuit where the power supply was connected, you place a wire. You're shorting that out. Every quarter, we do get a lot of questions and concerns about that. So I ensure to mention this in class, in a theory class, as well as the lab class. Okay. Shall we look at an example? All right, let's go ahead and do that. So example for superposition asks us to find the current I2 using the principle of superposition. Okay. So first thing, where is I2? On the far right. That is the current that is flowing through resistor R3 as well as resistor R2. We can see that they are in series. We can reduce them, but we won't, not yet. Not yet. If we count the number of nodes, 1, 2, 3, 4, we have 4 nodes. We can possibly reduce those 4 nodes to 3, right? 3 nodes, and we can apply node voltage analysis. Or we can see there are 2 meshes in there. We can apply mesh current analysis and find I2 that way, right? Superposition is 2 sources. You perform 2 separate analyses. You find the value of I2. The first time you find it due to solely VS active and IS inactive. And the second time you find it for the current source IS active and VS inactive. And the resulting current I2 would be a sum of both those values. Okay, so I2, I'm going to write this on the left. This actually comes at the end of the analysis. When you divide the circuit, you can label it whatever you want. I'm going to label the pieces as I2 due to VS and I2 due to IS. You can simply call it IX and IY. IA, IB, doesn't really matter. And I2 due to IS. Okay. I2 due to VS, I2 due to IS. So let's take the first case. First case is where VS active and IS inactive. Okay, VS is active, IS is inactive. VS is 10 volts, IS is 2 amps, R1 is 5 ohms, R2 is 2 ohms, and R3 is 4 ohms. So first thing when you're drawing the circuit for superposition is you draw out the circuit exactly as it is. You leave out all of the inactive sources. Again, remember, when you redraw the circuit, only one source is active. The rest of the sources should be inactive. In this case, there's only 2 sources, so it's easier. But if you have 3 sources, you're performing 3 independent analyses. Only one source is active, the other 2 are reduced to 0. If you have 4 sources, 1 is active and 3 are reduced to 0. Okay, yes. That's a judgment call. So again, the question being asked is when would we use superposition? That is kind of a judgment call. So if I was an engineer, I'm trying to analyze a circuit, I might try node voltage. And if I wish to verify my answer, I might use superposition. I might try mesh current. And again, if I wish to verify my answer, I could do superposition. If I saw, as personally, for me as an engineer, if I saw a circuit which has 3 sources or less, I might tend to use superposition, because the obvious downside is for every single quantity, you have to perform n number of analysis or n number of analyses. So if there are 3 sources and you wish to find one current, you have to analyze the circuit 3 times just for one quantity. So just for I2, you have to perform 2 separate analyses. If I wish to find VR1, voltage across resistor R1, or VR2, I have to again perform 2 separate analyses. Make sense? If it's 4 sources, 4 calculations for each single quantity. And you can 5 sources 5 times. So it gets very long. It's highly inefficient. It's very simple, but it's highly inefficient. And you can see where the inefficiency comes from, right? It's very time consuming because it gets longer and longer the more number of sources you have. So again, it would be a judgment call on when you would wish to use. But personally, for me, my limit would be like 3 sources or less. Make sense? And you can take these circuits, and if you wish to practice, you can analyze each circuit using all 3 techniques: node voltage, mesh current, and superposition. See if you can arrive at the exact same answer. So if students wish to practice, then you can take all of the circuits and all of the examples we did for node voltage, mesh current, series parallel analysis. You can apply all 3 techniques to the same circuit. Okay. All right. So redrawing the circuit with only Vs active, we draw the circuit exactly the way it is, except we are going to leave out Is. So we leave out Is, we have R1, R2, and we have R3. Now, Is inactive, meaning we have to remove Is and replace it with a open circuit. Effectively, we simply remove a current source. You don't even have to draw it out. No need to draw out the wires. You don't need to draw that branch, because once it's open, it's open. There's nothing else connected there, right? So we don't need to draw anything else. Simply open, and I have current I2 Vs flowing in that right branch. Excuse me. So a lot of allergies around right now. What do we see? Anytime you redraw the circuit, take 30 seconds, let it sink in. See how the circuit has changed. In this case, very easy to see. What do we see? I see nods, but I'm not hearing any words. I know my hearing is bad, but I don't think anyone is saying anything. All 3 are in series, right? R1, R2, and R3. The circuit changes. Every time it changes, you let it sink in. Take as much time as you need. I know it's easier for me to say, and it's hard for students to do, but take at least 30 seconds. Okay, if you're sitting in a 2-hour exam or 2.5-hour exam, 30 seconds is not that much time. For let it sink in, see what it is doing. In this case, it's very easy. I think at this point, I have confidence every student can recognize that this is a series circuit. The series circuit, the current through there is a result of the voltage source and the 3 resistors. One-step answer, I can write I2 due to Vs is simply given by Vs over Req. In this case, Req is R1 plus R2 plus R3, which is 10 volts divided by 5 plus 2 plus 4, 11 ohms. If you have a calculator, go ahead and calculate this and let me know if you arrive at the same answer. Yes, 0.909. Only half the work yet. We still need to analyze for IS. Does that make sense? Right. So let's look at the second case where you have IS active and VS inactive. And this time, again, we will, whichever sources are inactive, you leave them alone. You first draw the circuit diagram as it is without the sources. Voltage source Vs is inactive, reduced to 0, meaning we replace it with a short circuit wire. Think over this and let me know how the circuit changes. So again, redraw the circuit. Take your time, let it sink in. You can redraw it as many times as you need until it starts making sense. That's what I used to do as a student, and I always suggest that to all of my students. You redraw the circuit in a way that makes sense to you. But when you redraw it, you keep track of all the nodes and you keep track of all the components that are connected between those nodes. So what do we see? The major change is on the left side of the circuit. Right side of the circuit is as it is. On the left side of the circuit, we have R1 connected to IS. And then we see the other end of R1 is connected to the other end of IS. Both terminals of R1 are connected to the respective terminals of IS. So that means R1 is in parallel with IS. Here Vs is of course equal to 0. How about the right side of the circuit? R2 and R3? They are in series. That series combination is also in parallel with IS. You can draw one more time where IS is in parallel with R1 and R2 plus R3. Does that make sense to everyone? Right? If current source IS, and you have on the left side of the circuit, it's R1, and the right side of the circuit, it's R2 plus R3. They're all in parallel. Does everyone see that? So what technique comes to mind? The first and obvious technique that should come to mind is Ohm's law by default. Okay, always. You have two resistors in parallel. Can you combine them? Yes. we can find Req, one single resistance as seen by the current source Is. Apply Ohm's law, find the voltage across the current source. Because the current source is in parallel, that same voltage also appears across R1. It also appears across R2 plus R3. Apply Ohm's law one more time, you can find the current through R2 plus R3. If you want to take a shortcut, current is being divided. You can apply current division. Current is being divided, current division. In either case, you have to find Req. My Req is R1 in parallel with R2 plus R3. R1 is, what is it, 5 ohms in parallel with 4 plus 2, 6 ohms. 5 times 6 divided by 5 plus 6, 30 divided by 11. Gives us approximately 2.73 ohms. Apply current division. And I can find Is times Req divided by R2 plus R3. And the answer is surprising. The exact same value. Let's take a 10-second pause while you write it down and think over it. Let me know if you have any questions. Does that make sense? Yes? No? Are you thinking over it? So what is the final answer? Okay. How many of you agree? Yes? You all get a 0 in advance. That was kind of like a stupid pun, but yes, the answer is 0. Look at the direction of the current source. As I said, extract as much information as you can from the problem statement. That includes the circuit diagram. The circuit diagram would indicate the polarity of the voltages. It will also indicate the direction of the current. Is is flowing down. If it's flowing down, it comes down this way, contributes to a current going in the opposite direction. The blue arrow simply indicates that the problem wants us to find the current flowing in that direction. If a current direction is indicated in the problem statement, all it means is that you have a meter and you're measuring the voltage or current according to the indicated polarity or the current direction. In this case, the indicated direction is coming down from the top. Current flows from high to low, plus to minus. A multimeter or a digital current meter or a voltmeter also has 2 terminals, plus and minus. The tail end of the arrow is where the plus of the meter would be connected. And the arrow head is where the negative terminal would be connected. Current going from plus to minus. Arrow is going from left to right. If the arrow is going from left to right, left end is positive, right end, the arrowhead is negative. That is how you're measuring the current. That's all it means. It doesn't mean anything else. Again, if a voltage polarity or a current direction is indicated in a problem statement, and it's simply asking you, you are connecting a meter according to the indicated polarity or current direction, what are you measuring? That's all it is asking. If you were to perform this experiment in the lab and you connected a meter according to that blue arrow, the positive end would be at the tail end and the negative end of the meter would be the arrowhead. When you analyze this, you're simply looking at the actual current that IS is supplying, and IS is supplying current that's going in the opposite direction, so your meter will give you a negative sign. That's why I left some space in there. That's minus. That's all it means. Again, I just want it, it's not, to like be patronizing or condescending. I just wanted to use it as a teaching moment. Okay. This is just to get students into the mode of looking at circuits, looking at all parts of the problem statement of the circuit diagram. And so when we find I2, we have a sum of 0.909 and minus 0.909. And so I think somebody stated 0, you stated 0, so you get 100%. Again, there are no verbal quizzes, no verbal points, it's just a discussion. Okay. So the actual answer for I2 is 0 amps. So think over that. Let me know if you have any questions. Any questions? Does the procedure make sense? So yes. Yeah. If this was a physical circuit, all it would mean is that the voltage source Vs and the current source Is are both contributing enough energy that both ends of those terminals, R2 and R3, are the same exact equivalent potential. It might be 2 volts and 2 volts at both ends, but if it's 2 volts and 2 volts, exact same potential, no current flows through there. Theoretical analysis, we are saying that there's a current coming from the top and there's a current coming from the bottom, and so they result in 0. That's just theory. Mathematical analysis. Physically, in real life, if this was a real circuit, it would just mean that both ends are at the exact same potential. That means the potential difference between the 2 points is 0 volts, and hence no current would flow through. That's what it would mean. That makes sense? Fully. And every circuit is different. Every circuit is different. If you have like 3 sources, you can break it up into 3 different parts, 3 separate analyses, find the voltage, you add up all 3 of them together. That would be your actual voltage. You can apply node voltage analysis to this circuit, apply mesh current analysis, and see if you can arrive at the exact same answer. You know the answer to this problem, right? 0 amps. See if you can arrive at the same answer. That would be good practice. And it wouldn't take long. There are only 2 meshes in there, right? 2 meshes in there, 2 small equations. And it's the current source is in a shared branch, meaning you can get it I1 minus I2 equals 2 amps. 1 extra equation. So it's only 1 equation that would be required to solve this. You apply KVL in the outer loop, and that's it. Node voltage analysis, 3 nodes. Bottom node is your reference. You have the answer at the other end of the node. So again, 1 unknown, 1 equation, you should arrive at the answer easily. Right? Any questions? Yes. That's possible. So the Question being asked is, if there was a voltage source and a current source in the exact same line, what would we do? Well, it would depend on the circuit. It would depend on the circuit, see if there's anything else in the circuit or not, and then you would proceed with the analysis that way. Yeah. If you were to use, let's say, superposition for that, so it would be a voltage source in series with a current source. If the current source is active, then the voltage source is a short. Then it's supplying current through the rest of the circuit. If it's current source inactive, it would be open. The voltage source is connected, or it is disconnected from everything, so nothing is being supplied. So the answers would be 0 for voltage source. Okay, without looking at an actual circuit, that would be my guess. All right, any questions? Let's look at the homework problems then. Homework problem is on page 36. It's only 2 problems. This is a circuit you have seen before for node voltage, I believe. Majority of the superposition work is just applying the concept. You're breaking up the circuit. And so I will go over that right now. If it's only voltage source V active and current source is inactive, we ignore the ground. Ground is just a reference. You don't really care about it. So that would be the first. Current source is not there anymore. What can you say about R2 and R3? Connected at the bottom. So if they're connected at the bottom, they would be in series. And then you can redraw the circuit. A circuit like this, you can flip it to make them all vertical. If you flip it to make them all vertical, you can see R1 is in parallel with the voltage source, is in parallel with the 2 resistors, similar to the previous example. Instead of a current source, we have a voltage source. Makes our job easier. Combine all of them together, and you find the resulting current. And again, the indicated direction is simply the measurement direction. That's all. What is it? I1 or IS? I can't even see. IS, right? IS is indicated as flowing through the voltage source from left to right. It simply means you're connecting a meter to measure the current through the voltage source in that direction. That's all it means. And then when the current source is connected, let's try afterwards. Voltage source is replaced with a short, current source is active. This is the reason I wanted to cover this in class. I'll wait until everyone finishes writing down. So again, when you redraw the circuit, take a few seconds, let it sink in. See how the circuit has changed. Okay, see how the circuit changes. So in this case, the circuit has changed because the voltage source is in parallel with R1. Voltage source is now a wire. A wire has 0 ohm resistance. If it has a 0 ohm resistance, anything connected in parallel with that wire is effectively redundant. It is removed from the circuit because it has no effect on the rest of the circuit. Again, a wire has 0 ohm resistance. Current will always take the path of least resistance. 0 ohm is the lowest value. With 0 ohm resistance, that means that anything that is in parallel with that wire is effectively not part of the circuit anymore. So R1 is effectively disconnected from the rest of the circuit because it doesn't have any effect on the circuit. And that is an important concept in electrical engineering. Okay? If you have a wire, anything in parallel with that wire is redundant or does not have any effect on the circuit. So again, when the circuit changes, let it sink in, look at the nodes, see what is connected between each and every node. Remember these concepts, and then you can apply your techniques. Yes. Anything that's in parallel. If there's a voltage source across it, the voltage source is shorted out. In real life, you'd have a spark and an explosion. Yes. So the ground in terms of the circuit is simply a reference point. You are measuring the voltage V1 and V2 with that reference point. That's all it means in this case. It's not interfering with the circuit operation. Doesn't matter where you connect the ground in the circuit, the voltage source and the current source will still see R2 and R3. Because so the question being asked is, if the ground is connecting at the bottom node, how is it affecting the circuit? The answer is, it doesn't affect the circuit at all. It is simply marking the point of reference for V1 and V2, meaning V1 is being measured with ground, V2 is also being measured with reference to that ground point, which is right here at the bottom. That's all it means. Connecting a ground anywhere in the circuit is not going to change the resistance, right? Is it changing the value of R2? No. Value of R3? No. Value of R1? No. So Req as seen by the voltage source remains the same. Req as seen by the current source also remains the same. If we flip the ground and we connect it somewhere here, R1, R2, R3 will still have the same values. Req as seen by the voltage source and the current source will remain exactly the same. It is simply indicating the point of reference for voltage measurements. That's all it's doing. Okay. But coming back to the second circuit where current source is active, what do we see? R1 is removed from the circuit. You only have R2 and R3 in parallel with the current source. It's the exact same circuit as the previous example. So this is more than half the solution. Okay? You have superposition, you break it up into individual pieces, and then you think about how you would analyze this. But that's half the work. Actually, more than half the work is done. Because after that point, you can apply any analysis technique you want. So under superposition, you can apply node voltage, mesh current, series parallel analysis, Ohm's law, KVL, KCL, anything you want, okay, depending on the circuit. But if it's superposition, you break it up first into individual pieces. Here we have two sources, so two individual pieces, analyze each circuit independently, add them up, and you have your final answer. Does that make sense? Right? In the second one, two current sources. Everything's in parallel. Not much to think about. Straightforward. The only thing you have to account for is the current directions. That's it. So there are no other hints that I can give for problem number 2. As I said, if the next hour is free for you, free as in like, if you don't have a class, you can sit down and knock this out right now in less than 30 minutes. Okay, that way your Saturday and Sunday will be free from circuit analysis at least. The only thing you will be studying is Sunday night for mesh current analysis quiz on Monday morning. Not yet done. We still have a few minutes. Yes. No. So mesh current analysis on the quiz on Monday, and I will post an announcement sometime later today. Again, indicating the same thing. 6 minutes left. I want to introduce a topic. Yes. Not necessarily. It could change depending on what the direction is. So the question being asked is, if it's just voltage source that is active, would it always be positive? The answer is no. It could be any, it could be any value, it could be any sign. Just depends on what the polarity is that is given to us. Okay. So let's say you are a design engineer in your own field, and you're asked to find the value of R6. You are asked to find R6 so that VR6, the voltage across R6, fits a certain spec. Let's say this is like a small circuit board that drives like a large piece of machinery. That machinery could be something, right? Could be something, could be anything. But you need VR6 to be 2.5 volts, maybe plus minus 10%, but it should not exceed that spec. The rest of the circuit is already done. The rest of the circuit has fixed values. It has fixed components. You have multiple sources in there. You have multiple resistors in there. Your job as an engineer is to determine the value of R6 so that it does not exceed or does not fall below 2.5 volts. What do? You perform an analysis on this technique. You don't need to write anything down. This is simply an explanation purpose, right? It's a random circuit. You could choose node voltage analysis, or you could choose mesh current analysis, or you could choose superposition, and you can arrive at a value for R6, right? Let's say VR6 in that case, you chose R as, let's say, 50 ohms, for instance, and you obtained VR6 as 2.6 volts. Large resistance, higher voltage. Doesn't fall within the spec. So you rerun the simulation with a different value of R6, which is, let's say, you go to 30 ohms. Now VR6 has fallen below, and you might get 2.4 volts. So you try a different third value, and a fourth value, and a fifth value. So you perform multiple calculations, multiple analyses until you arrive at a value of R6 that would make VR6 fall within a certain spec, right? Well, in order to avoid doing that, there was a theory. This theory was postulated by a French telegraph engineer in the late 1800s by the name of Leon Charles Thevenin. The theory states you could take a large circuit like this one, exclude R6 from your analysis, and you can represent that entire circuit, a linear circuit comprising of independent sources and linear resistors, and you could represent that entire circuit as a single voltage source. A single voltage source in series with a resistance. That theorem is one of the most important concepts in circuit analysis, and it's known as Thevenin theorem. And basically, it is saying that this small circuit with one source and one resistor is equivalent to that larger circuit between the terminals of analysis. The terminals of analysis would be excluding R6. And so right here. So you would analyze the circuit once and only once between the pair of terminals where R6 was connected. And you could represent that entire circuit with an equivalent single voltage in series with a single resistor. That voltage is known as the Thevenin voltage. The theorem is known as Thevenin theorem. And RTH is known as the Thevenin resistance. It is one of the most important concepts in circuit analysis. Okay. And now VR6 is a one-step answer, because VTH and RTH do not change. So you could take multiple values of R6 and plug it into this equation and calculate VR6 as many times as you need. But the large circuit is analyzed only once. You find the Thevenin voltage, you find the Thevenin resistance, and that's it. all other values of R6 can be determined in one step. That, in short, is Thevenin theorem. We are almost out of time, actually out of time. But one more thing is, taking this concept further, a few decades later, there was a American engineer by the name of Edward Norton, same name as the actor. He postulated his own theory saying that you could take that large circuit and represent it as a single current source. And that current source is named as Norton current, and the theorem is known as Norton theorem. So Norton current. And both those circuits are equivalent to that larger circuit. So having said that, we'll end class here today, and I will see you all on Monday. I will have student hours or student meeting hours this afternoon. So if you need any help, stop by. If you can't stop by, you want to wish to see me over Zoom, I'll be happy to see you over Zoom. If you have any questions, send me an email. And I'll bid you all a good weekend. Oh, just a second.